In this final section of the semester, we want to look at friction and understand the difference between static and kinetic friction and how we go about using the coefficient of friction in solving problems. There are two types of friction when we deal with the force of friction. The first type that we deal with is static friction. Static friction is the force that one object exerts on another to prevent it from sliding. The objects are not moving relative to one another. The force is always parallel to the surface that's in contact and opposes the motion. And you must have a normal force for there to be a frictional force, and it must be an object that would slide if there were not some sort of frictional force that would be moving. Common examples of static friction are trying to move across a surface and having the object not slide, like when you're walking. When you're walking, you press against the ground with your foot. The bottom of your shoe and the ground have a static friction force to keep your foot from sliding. If your foot starts sliding, you start slipping, that would not be static friction anymore. The same thing is complicated to as tires. You want your tires to have static friction. If the tire rolls and touches the ground, it will hit the ground and not move relative to the ground. It's not sliding, it's staying in place. And then as it rolls, moving forward, but the actual contact is static friction. If it's not static friction, the tire is sliding across the surface, that's what we call skidding, and it becomes a lot harder to stop because we actually find the static friction force is larger than the kinetic friction force. Kinetic friction is the force that one object exerts on another when they are actually moving relative to one another, sliding across the surface. It's the same as static, it's parallel to the surface and opposes motion, but it's always going to be smaller force, and you're going to be dealing with two objects relative to each other. Skidding, your foot slipping, those kind of things are kinetic friction. When you pulled the box across the table in your lab, that was generally kinetic friction for the majority of the time. Static friction before it started moving, and then kinetic friction once it was moving across the table. This only occurs with the normal force that you have object sliding across the surface. You'll get a coefficient of friction. The coefficient of friction is an important variable for us to use when dealing with frictional force. The relationship that we're always going to use is the force of friction is the coefficient of friction times the normal force. The normal force is always that force perpendicular to the surface that is in contact. The coefficient does not have specific units. If it's kinetic friction, we'd use the coefficient of kinetic friction. If it's static friction, we use the coefficient of static friction. It's a number. It would be less than 1. It tells us what amount of the normal force is frictional force. So the frictional force and normal force will always be proportional to one another, with the frictional force generally being slightly smaller since the coefficient is less than 1. Here's an example coefficient of friction. One of the surfaces that has the highest coefficient of friction of anything we deal with is Velcro. Velcro is the case you see here where you have a coefficient of friction greater than 1. Try to slide Velcro across itself and it is almost impossible, and you get this coefficient of friction of 6. Most surfaces are easier than that, and we get coefficient of friction less than 1. Next highest one on this list is a smooth tire. So if you think of a race car tire, completely smooth, has a very high coefficient of static friction. Coefficient. Here that the kinetic friction is lower than the static friction. A groove tire is at 0.7 compared to the 0.9 for a smooth tire. So you think, well, why do we use groove tires? Because we want as much friction as possible. We want the tires to grip the road as much as possible. So smooth tires would make more sense. Smooth tires for this exact reason. The corollary when we deal with wet surface. If you look at smooth tire on dry versus smooth on wet, grooved on dry versus grooved on wet. A grooved tire has a 0.7 coefficient of static friction on dry pavement, but 0.4 on wet pavement. It's hard to stop when the road is wet. However, if you take a smooth tire, 0.9, higher coefficient of friction, better frictional force, better traction of the tires, on dry pavement, when you put them on wet pavement, it becomes 0.2. so almost no friction. That's why smooth tires don't work well at all on a wet surface. What the groove actually does is it pushes that down against the road, the water gets pushed up into the grooves, allowing the rubber to come in contact with the road. When you have a smooth tire, there's nowhere for the water to go. It forms a film between the tire and the road, and the tire starts to almost hydroplane in that case. That's why race cars are not driven in the rain. There are a few race car series, like Formula One over mostly in Europe, that does occasionally drive in the rain, but when they do drive in the rain, they switch to grooved tires. Grooved tires have significantly better coefficient than smooth tires on wet pavement. You see the example here, you have oil in your car. In your car, you have metal. The coefficient of friction will be 0.4 for kinetic sliding, but when it's liquid with oil, you get it down to 0.05, much lower coefficient of friction, so the metal parts don't have friction against each other of any significant amount, and you don't cause heat and slow down the engine and cause the engine to fall apart. And Teflon is one of those surfaces that has an incredibly low coefficient of friction. Teflon is used as a non-stick coating on a number of things. So this gives you some idea of what typical coefficient of friction looks like for static and kinetic on many different substances. And the coefficient of friction is going to be unique for the two substances that are in contact. When we think about our free body diagrams, if we had a car tire driving across the road, we're going to have gravity, we're going to have, or let's do your foot against the ground. You're going to have a normal force. You're going to be pushing backwards against the ground, so the ground's going to be pushing you forwards, and you're going to have a frictional force. So this could be your tire, this could be a box sliding across the ground. Now, a couple of key things to remember here before we get into solving problems. Remember, Fg equals mg, and if we have something sitting on the surface, it's not accelerating up and down, the force gravity down and the force normal up will be equal. So if I can find this force of gravity here, I know my force normal here, and then I know force of friction is the coefficient times that normal force. So once I have this force, I'll know this force, and from this force and the coefficient of friction, I can find the force of friction. So just by having the mass of the object on a surface not accelerating up or down, I can find 3 of the 4 forces in this diagram, and that will be very useful to us when we get into solving problems. Tomorrow night's video will cover some example problems of force of friction, and please remember to bring a copy of your notes for this video with you to class tomorrow.